Today we will look at some problems about unsteady radial flow to a well. For the first problem, a confined aquifer has a transmissivity of 500 square meter per day and a storage coefficient of 0.0005. Wells 1 and 2 completely penetrate this aquifer and will be pumped at a constant rates of 600 cubic meter per day and 1400 cubic meter per day respectively. Pumping will start in both wells at the same time. An observation well is located 400 meters from well 1 and 500 meters from well 2. And we need to determine how long can the two wells be pumped without exceeding a 1 meter drawdown limit in the observation well. At that limit, what is the drawdown contribution of each well? So for this problem, we will use superposition for unsteady flow in an aquifer with multiple wells at the same start time. So from this problem, we know the Q1 is 600 cubic meter per day and R1 equals 400 meters. And the T is 500 square meter per day, and the storage coefficient is 0.005. The Q2 equals 1400 cubic meters per day, and R2 is 500 meters. And based on equation 7.27, 7.26, and table 7.3 in textbook, we can create a table like this one. Let's look at the first three rows. And T is the time, the unit is day. So T is from day 1 to day 3. And after we know the time and all these values, we can use this equation to determine the column U1 and the column U2. This equation is equation 7.27 in the textbook. And after determining the U1 and U2, we can use table 7.3 to determine the W of U1 and W of U2, so we can determine the values in these two columns. And then for column S1 and S2, we can use these equations to determine the values. So this equation is equation 7.26 in the textbook. And now we can determine S1 plus S2. S1 plus S2 indicates a drawdown in the observation well. So we can see when T equals 2 days, the drawdown in the observation well is less than 1 meters. And when T equals 3 days, the drawdown is greater than 1 meters. So after using a linear interpolation, we can determine that when T equals 2.2 days, the drawdown in the observation well is 1 meters. And then we can use these equations and the table to determine the S1 and the S2. So now we can get a conclusion. After 2.2 days, the drawdown limits at the observation well is reached with S1 equals 0.33 meters and S2 equals 0.637 meters. So we finished this problem. For the second problem, we need to determine the drawdown at a critical location in a confined aquifer. The aquifer will be affected by two completely penetrating wells, both of which will be pumped at 207 gallons per minute. However, pumping from the second well will start a day and a half after the first well. And we know the distance between the second well and the point of interest is 279 feet, and the distance between the first well and the point of interest is 322 feet. And we need to determine the drawdown at a point of interest 3 days after the pumping begins in the first well if the aquifer transmissivity is 450 square feet per hour and the storage coefficient is 0.0005. First, we will convert the unit of discharge from the gallons per minute to cubic feet per hour. So we know the Q equals 207 gallons per minute times the 1 CFS divided by the 449 gallons per minute times 13600 second divided by 1 hour. So we know the Q should be equal to the 1660 cubic feet per hour. And then we apply equation 7.27 in the textbook for well 1. And we know the U1 should be equal to R1 squared times S divided by the 4 times transmissivity times the time. And we know the R1 is 322 feet. S is 0.0005. And the T is 450 square feet per hour. And we know the time should be equal to 3 days. And also equals 72 hours. So now we can determine that the U1 should be equal to 4 times 10 to the power of negative 4. And the from table 7.3 in the textbook, and we can determine that the W of U1 should be equal to the 7.247. And then apply equation 7.26. So we know this 1 should be equal to the 1 divided by the 4 times pi times transmissivity times Q1 times W of U1. And we know the Q1 is 1660 cubic feet per hour, and the W of U1 equals 7.247, and the T is 450 square feet per hour. So we can determine that S1 should be equal to the 2.13 feet. And then we need to apply equation 7.27 for the well 2. And we know the U2 should be equal to the R2 squared times S divided by the 4 times transmissivity times the time. And we know that R2 should be equal to 279 feet. S is 0.0005. And T is 450 square feet per hour. And now the time should be equal to the 1.5 days. Since we know the second will start a day and a half after the first well. So now the time should be equal to 1.5 days, also equal to 36 hours. So now we can determine the U2 should be equal to 6.10 times 10 to the power of -4. And again, from table 7.3 in the textbook, we can determine that the W of U2 should be equal to 6.842. And again, we know S2 should be equal to the 1 divided by the 4 times pi times transmissivity times Q2 times W of U2. And we know that Q2 should be equal to Q1 equal to 1660 cubic feet per hour. And we know W of U2 is 6.842. And we know transmissivity T is 450 square feet per hour. So now we can determine that the S2 should be equal to the 2.101 feet. And now we can determine the drawdown. The S should be equal to S1 plus S2 equals 2.13 plus 2.01. So we determine that, the S should be equal to 4.14 feet. So we finished this problem. For the third problem, a discharge while penetrating a confined aquifer will be pumped at a rate of 800 cubic meter per hour for 2 days, and then the pumping rate will be reduced to 500 cubic meter per hour. And the aquifer transmissivity is 40 square meter per hour, and the storage coefficient is 0.00025. And we need to determine the drawdown at a location 50 meters from the pumped well 3 days after the pumping has started. So since the well discharge is not constant during the period, so we apply equation 7.24 and equation 7.25 in a textbook, and with the N is 2 and Q0 as the beginning, the discharge is 0. And we know Q1 is 800 cubic meter per hour, and the Q2 is 500 cubic meter per hour, and the T sub 0 is 0, and the T1 equals 48 hours. And then by using equation 7.25 for K is 1, we can determine that U1 should be equal to R1 squared times S divided by the 4 times transmissivity times the T minus T0. And we know R1 is 15 meters and the S is 0.00025. And transmissivity is 40 square meter per hour. And the T is 3 days, so it is 22 hours. And T0 is 0. So now you can determine that the U1 is 5.43 times 10 to the power of -5. And then we know the U1 is 5.43 times 10 to the power of -5. And from the table 7.3 in the textbook, we can determine that the W of U1 is 9.248. And for K equals 2, we know the U2 should be equal to R2 squared times S divided by the 4 times transmissivity times the T minus T1. And we know R2 equals R1 equals 15 meters. The S is 0.00025. We know the T is 40 square meter per hour. And T is 72 hours. And the T1 is 2 days, is 48 hours. So now we can determine that the U2 is 1.763 times 10 to the power of -4. And from the table 7.3, we can determine that W of U2 is 8.196. And then we're using equation 7.24, and we know the S should be equal to the 1/4 times pi times transmissivity. Times transmissivity times Q1 minus Q0 times W of U1 plus Q2 minus Q1 times W of U2. And we know the Q1 is 800 cubic meter per hour, and the Q0 is 0, and the Q2 is 500 cubic meter per hour. And we also know W of U1 is 9.248. 248. W of U2 is 8.196. So now we can determine that S, the drawdown, is 9.83 meters. We finished this problem. For this problem, the characteristics of a confined aquifer are required. A pump test is conducted at a flow rate of 5.4 cubic meter per hour. Drawdowns are measured at an observation well located 80 meters from the pumped well and tabulate below. We need to determine the aquifer transmissivity, the storage coefficient, and the drawdown after 50 hours. So we can use this table to create a figure like this one. And then we pick t equals 1 hour and t equals 10 hours. So we know this is delta log t. So it is 1, and we know this is delta s. And from this table, we can determine that the delta s should be equal to 1.61 meters minus 1.09 meters. So it is 0.52 meters. And then, the t should be equal to 2.3 times qw divided by the 4 pi times delta log t divided by the delta s. qw from this problem is 5.4 cubic meters per hour, and delta log t is 1, and the delta s equals 0.52 meters. So we can determine that the t should be equal to 1.9 square meter per hour. And from this figure, we have T0 is 0.0082. So T0 is 0.0082. And we know the storage coefficient S should be equal to the 2.25 times transmissivity times T0 divided by the R square. The T is 1.9 square meter per hour, and T0 is 0.0082. And from problem, we know R is 18 meters. So we can determine that the storage coefficient S should be equal to 1.08 times 10 to the power of negative 4. And then from equation 7.40 in the textbook, we know the drawdown S should be equal to 2.3 times QW divided by the 4 times pi times transmissivity. And times log 2.25 times transmissivity times time divided by the R square times the storage coefficient. And this QW is 5.4 cubic meters per hour. And transmissivity we determined before is 1.9 square meter per hour. And the storage coefficient is 1.08 times 10 to the power negative 4. And the time is 50 hours. And the R is 18 meters. So now we can determine that The drawdown is 1.97 meters. We finished this problem. For the fifth problem, a factory is pumping 1.55 CFS from a confined aquifer and 16 feet from a fully penetrating river, and an observation well located between the river and a pumped well 100 feet from the river and 16 feet from the discharge well, and registers a drawdown of 0.333 feet. We need to determine the transmissibility of the confined aquifer. So actually, this problem is very similar to the example 7.50 in the textbook, and we will use this figure to solve this problem. And this is well A, and this is well B, and we know it is a recharge well. And from the problem, we know the P should be equal to the 16 feet. And we will apply equation 7.12a in the textbook. And we know the S should be equal to the SOB plus the QA divided by the 2 pi times T times the natural log of RAO divided by RA plus the QB divided by the 2 pi times T times the natural log of RBO divided by RB. And we know the observation well in this case had a drawdown of 0.333 feet. 3 feet. So we know the SOB should be equal to the 0.333 feet. And we also know that the drawdown at the river boundary should be equal to 0. So S should be equal to 0 feet. So we know S should be equal to the 0 feet. And from the problem, we know the QA should be equal to the 1.55 CFS, and the QB should be equal to the negative 1.55 CFS, since the well B is a recharge well. And so RAO should be equal to the 16 feet minus 100 feet. That equals 16 feet. Distance from the well A to the observation well. So this is 16 feet. And RA should be equal to the 16 feet. And RBO should be equal to 16 feet plus 100 feet. So it is 760 feet. So the distance between the observation well and the well B, so it is 16 feet. And this RB should be equal to the P, so it is 16 feet. So now we can determine the transmissibility of the confined aquifer. So can determine that the transmissibility T should be equal to the 0.0262 square feet per second. We finished this problem. For the last problem, a centrifugal pump is required to dispose of the water seeping through the earth levee depicted in this figure, And using the flow net provided, find the seepage rate in gallons per minute. We know the water level behind the levee is 30 feet and it is 980 feet long. And the permeability coefficient of the soil is 7.5 times 10 to the power of negative 6 feet per second with a porosity of 0.4. To solve this problem, we will apply equation 7.56 in the textbook, and we know the Q should be equal to the K times M divided by the N times H. And from this problem, we know the K is 7.5 times 10 to the power of negative 6 feet per second. And the M is the number of flow channels. So from the figure, the M should be equal to, this is 1, 2, 3, 4. So we can determine that the M is 4. And the N is the number of equipotential drops. From this figure, we can determine that the N is 30. Since we know this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So N is 30. And we also know the H is 30 feet. So now we can determine that the Q is 3 times 10 to the power of negative 5 CFS per feet. And for fullness of the levee, the seepage rate is Q equals 3 times 10 to the power of negative 5 CFS per feet times 980 feet times 449 gallons per minute per 1 CFS. So we can determine that the seepage rate Q is 13.2 gallons per minute. We finished this problem.